Hello, hi, welcome back everyone. Hello, thank you so much for clicking on today's video. Just a quick little introduction. I'm sure many of those watching are my own students. So hello, my name is Sophia. I am a select entry tutor, and today's video will be a continuation of the previous video on cyclic patterns. However, today's video will focus more specifically on Gauss's formula and cyclic exponents. So first, before we actually get into proper content, I really want everyone to think about the key principles and ideas that underpin all our cyclic patterns. Okay? We are going to have a look at Gauss and we're going to have a look at cyclic exponents because we know that these come up very often in select entry exams, in scholarship exams, in ACER style papers. However, this exact formula might not show up in exactly the same way in every single exam. It might look a little different. They might put a little twist on it in the exam. They might change it up a bit this year, is what I'm saying. But what I really just want everyone to be very conscious of, and what you need to be conscious of to be successful in this exam, is when you come across a question and it looks really finicky, it looks like it's going to be a lot of work to do manually, that you realize, oh, that's a bit of a red flag. Alarm bells should go off in your mind, and you should immediately consider if there are going to be any easier or more reasonable ways to do the problem. Okay? So what we go through today, Gauss's formula and cyclic exponents, the main things that these two formulas and the tricks we're going to learn today allow us to do is to do questions a little bit more quickly. Questions that otherwise would take a lot of manual labor, a lot of arithmetic heavy lifting to do, they allow us to do in a really quick, clear, succinct sort of way. But will this exact formula show up on the exam? Hopefully it does. Hopefully you watched this video and it wasn't for nothing. But the main thing you really want to take away from this video is if I see something that looks a little too annoying, something that looks like a little bit too much work, you actually take a step back for a moment. You can take a moment, take a deep breath, and actually consider, hey, is there going to be any easier way to do this problem? That's going to be the thing that will really help you out. Of course, alongside learning the tips and tricks we'll go over today. So let's get started and let's have a look through. So the typical examples where you're going to apply Gauss's formula is usually when a question is phrased something along these lines, or we have to deal with something that asks us to find the sum of some set of consecutive numbers. Consecutive meaning in a row. So if someone asks you to add up 1, 2, 3, 4, all the way up until 100, or someone asks you to add up 20 plus 30 plus 40, so on and so forth. So any situation where you have to add a lot of numbers together, typically them being in a row or them having some sort of pattern together, that's when we're going to use Gauss's formula. With cyclic exponents, the examples are a little bit more limited to compared to Gauss. Usually, it's just going to involve some number being raised to a large exponent. If you're having a very nice examiner, whoever's written the exam paper, if they're feeling a bit nice that day, it might just be very simple. They might just ask you 3 to the power of 1000 or something crazy like that. However, the other worded scenario where you're probably going to see cyclic exponents being asked of you is cases where you have a lot of repetition going on, something timesing itself again and again, because that, in other words, just means something is raised to a certain power. So any cases where you have repetition, a lot of rounds going on, that often is going to be a cyclic exponent style question. But the most obvious example where you're going to be asked to, or the most obvious kind of question they can ask you where you need to apply cyclic exponents is when you have a huge number raised to a huge exponent, something along those lines. So key takeaway, you see large numbers, you see something that's going to pose a lot of inconvenience to you, you see some sort of pattern, it could be one of these two things, okay? So we really want to be able to spot it first, okay? It's very good to know how to use these things, but we have to know when to use them as well. So that's why I'm just starting with typical examples. Let's move on from here. Now, I'll just tell everyone a quick little story in case this helps anyone remember the formula a little bit better. So, Gauss's formula, it's named after this mathematician, this lovely gentleman we see over here, Carl Friedrich Gauss. He was from the 1700s and he was a child prodigy. The little story that goes alongside Gauss's formula is that his maths teacher had asked the class to solve 1 plus 2 plus 3 all the way up until plus 98, plus 99, plus 100 as a bit of a busy work kind of task. But Friedrich Gauss, because he is a child prodigy, he's a genius, he was able to solve the question very quickly without having to do very much manual work at all. So we'll now take a look at how he managed to achieve such a feat. Okay, so the formula itself goes like this. It's n times m plus 1 divided by 2. N represents the number of numbers. Okay, so back in the 1700s, when Mr. Gauss was asked to add 1 all the way up until 100, this is the rough formula or idea he used. And I'll show everyone a proof of where it comes from as well, just so you have some further understanding and an idea of how it all works. So let's list out a few of the numbers. Now, in the exam, I might not be writing out as many numbers as I am over here, but it's always good to just start with a bit of a sample just so we can at least see what's going on. So I've written 5 numbers on the smaller side starting from 1 and 5 numbers starting from the larger side over here as well, going back from 100. So the proof for this essentially is that we take our very smallest number, which is 1, and we take our very largest number, which is 100, and we add them up over here, like so. Okay, from there, we get 101. Okay, cool. Let's now do our second smallest number with our second largest. So 2 plus 99. Okay, oh, we get 101 again. So that's looking good, interesting. We'll do another number. Let's do 3 and 90. Oh, I accidentally left out 97 when I was writing there. My apologies, everybody. Let's do 3 and 98. Okay, and we get 101 again. And 4 and 97, and we get 101 again and again and again. Now, we might ask ourselves, how come? How does this work? Why do we always keep getting 101? Well, it makes sense because we start off with 1 and 100. That's sort of our standard or first one. Then look to your next calculation here. You see the smaller number increased by 1, but the bigger number, the 100, it decreased by 1. And so it kind of balances out, comes back to be 101. That makes sense. Same thing when we progress to the next set, 3. Okay, so here it's 1 bigger on the smaller number side, but it's also 1 smaller on the larger number side. And so because of that, it'll just end up balancing out. Okay, so what you can now imagine is we are going to get dozens and dozens and dozens of pairs of 101. Sometimes you might see some teachers draw it up like this as well. They might go 1 and 100. They make 101. And next, 2 and 99. And I'll use a different color, 3 and 98. 4 and 97 up here. 5 and 96, and so on and so forth. Okay, and so you see they sort of join up over here. And so you can imagine that this would continue all the way until we meet in the middle, with the final pair being 50 plus 51, and you get 101. Okay, so essentially we get heaps and heaps and heaps of pairs of 101. We know we get 50 pairs of 101 as well, because from 1 to 100, we have 100 numbers. A pair, by definition, a pair is 2. Okay, so we get 50 pairs of 101. Okay, that's where the formula really comes from. Okay, but we actually prefer to usually use a formula like this because this one is a quite nice one, 1 to 100. It's nice and smooth. However, in some scenarios, when you have an odd number of numbers, and we talked about this in the last video, in case anyone is a bit unsure how to find the number of numbers within a range, how many are odd, how many are even, we went over all of that in the last video. So have a look at that if you're a little unsure, and then come back here if you're feeling unclear on that. But between 1 to 100, we have 100 numbers. That's all good. But what if it's 1 to 101? Okay. Well, there's an issue there because from 1 to 101, there are a total of 101 numbers. Unfortunately, this is also an odd number and pairs come in twos. So, what you're going to end up with is yes, we'll have a bunch of pairs as well that continue on. However, we're going to have some odd number right there in the middle. And that's where we sometimes see students having a bit of trouble when they're under exam and test conditions. Sometimes when students get really stressed out, they can't actually figure out what the middle number is. Here, from 1 to 101, I think it's still relatively easy. I think most people can still figure out what that middle number is. But sometimes, and you'll see this later on in the video as well, when we have ranges that are a bit funny looking, 40 to 97, 102 to 3000 or something like that, it's a little trickier for students under exam conditions to figure out what that missing middle odd number is, and that's when we see a lot of mistakes. So that's why we actually prefer to use a formula like this. Okay, so I will show everyone how to apply the formula as well. In this case, there are 100 numbers. Here, I write 101 and on top of 2. Now, here's a little trick, everybody. For me, I actually know that I'm someone who's very clumsy at arithmetic. My own students know this as well. All the time in class, I can solve these really hard problems. I can sketch these really tricky graphs. But at the end of the day, it's usually a multiplication or a division, addition, subtraction that ends up getting me, unfortunately, quite embarrassingly. So over here, I honestly know if I do 100 times 101, I might mess something up. So what I like to do is I like to simplify earlier on. The earlier that you simplify, the better, because now I just have to do 50 times 101, and if fate is on my side, I hopefully shouldn't mess this up on a good day. Okay, I get 5050, which looks very correct to me, so that is good. Okay, so there's that. Now, by the way, this proof, it's very handy. I really would recommend that even though you're not going to be asked in the SLET entry exam to do a full-blown proof, that you do take a moment to fully understand what's going on over here. So that if they ask you a question that's a bit of a twist on Gauss, or you might have to do something kind of similar but kind of different, you actually know the ideas that underpin this big fancy formula here, and you might have to you can create something like this on your own if you really needed to in some sort of scenario. Okay, you still want to understand the proof, and you want to actually be able to explain that to someone else if they ask you as well. Okay, let's move on from there. Now, let's talk about Gauss in select entry as well. So our typical kind of question is we'll get add up from X to Y. Oh, all the numbers from 1 to 100, from 50 to 1000, and so on and so forth. Okay, that's our most obvious kind, which we can address. Okay, we also have two other examples where this can come up. So sometimes it can be more subtle. Sometimes it could be some sort of pattern difference. Now, what I mean by that is we may have a case where, for example, from 1, we might have a pattern, so the series of numbers, one after another. It might go 1, 2, so these have a difference of 1. And then you might have, 4 over here, so this is now plus 2. Then you might have 7, plus 3, and so on and so forth. They could potentially ask you to apply Gauss in one of these patterns. They could ask you maybe what the 50th number over here is, or what the 70th number is. And so what you're then going to need to figure out is, well, if we go all the way up until the 70th number plus 70, how much are we adding on all at once? You might consider that. And you might have to remix that with a few things I went over in the previous video on cyclic patterns. That's another way you can be asked to do it. Okay, another just sort of general application of Gauss is you might just have to add up numbers with a regular pattern very quickly. Okay, they could be asking you some sort of question on the average or the mean. They might give you a whole set of numbers, okay? They might actually give you all the numbers from 1 to 100 or from 1 to 20 or so on. Imagine if you had a series of numbers. Let me just list out a few, right? Imagine if they just had even 10 numbers. Let's not even talk about 20. If someone is actually sitting there and they're counting them up one by one, yes, it's doable, but two things. Number one, it might take up a lot of your time. And number two, you're probably going to make a mistake. I know if it was me, and definitely Sophia in year 8, would have for sure made a mistake adding up all numbers from 1 to 10 when she was placed under a lot of stress. Okay, so you could be asked to do this, and someone could ask you, hey, what's the mean of this set of numbers, or something like that. Okay, and you would be able to quickly total it up and then find the mean. In this particular case, actually, this is a bit of a side note away from Gauss. If you're given a set of consecutive numbers and you're asked to find the mean and the median will just be whatever the middle numbers are. So I can actually tell you the mean of this set of numbers would be 5.5. Okay, but it could be another example. It could be the numbers are maybe like 2, 6, 8, so on and so forth. And then you've got some other numbers on the other end that are equally spaced apart. You can use a bit of Gauss. You can go, oh, smallest number plus biggest number, second smallest plus the second biggest, and so on. As long as there's a consistent sort of pattern there. You can't do that if it's just some random scattering of numbers. But if you do see some sort of consistent pattern there, you can apply it. Okay. Now, another example to be really aware of is Gauss, but in a particular range. So this is where, unfortunately, I see a lot of students making some mistakes. Okay, so they might ask you to do something along the lines of this. You might have to add up all the numbers from 26 to 109. Okay, they could give that in some sort of worded equation. They could just ask you to do that up front. They could ask you to do a question. This is kind of similar to an Olympiad question from many years ago. They could say, oh, there's a bunch of people with letter boxes along the street, and they're 26, 27, 28, so on. They could ask you, oh, what's going to be the sum of all those letter boxes? They could ask you, oh, how many letters, numbers they have to purchase. They could ask you something along those lines. Okay, but anyways, you might have to do something like this. Now, this is not good for us because we're used to n times n plus 1 on 2. But we know that if we wanted to find the total from 1 to 109, we would go 109 times 110 divided by 2. But now we have this pesky little range over here. We have all this stuff before the 26 as well. So we have to sit down for a moment and we have to consider, well, how are we going to deal with this? How are we going to make sure that we count up exactly what we want? Well, let's start off by doing a little experiment once again, guys. I will just list out a little bit of the pattern just so we can see what's going on over here. Okay? So 1 plus 2 plus 3 plus 4. I'm going to do dot, dot, dot to show some numbers are passing. Plus 24 plus 25 plus 26. Okay. And then all the way dot, dot, dot 109. Okay. Now here's the range that we're interested in. We're really interested to see 26 plus 27 all the way blah, blah, blah up until 109. What we're very disinterested in is this range over here. Unfortunately, no one cares about 1 all the way up until 25. In fact, we want to get rid of the set from 1 to 25, okay? And that's exactly what we're going to do. What we're first going to do, everyone, in our pattern is we're just going to find the sum from 1 to 109, which, if you were listening earlier, hopefully everyone can do that by just plugging it into the n times n plus 1 on 2 formula. What we're going to do after is we're going to take away that green part. We're going to take away the green bits I've highlighted, and then we will be left with only this desirable section, okay? Now, you might be thinking, well, what's the formula for this? Now, there are some formulas, and if you search up online, there are a few floating around. But I really prefer to use a bit more common sense. So I'm going to give you guys a little bit more of a haphazard formula, but it's one that works, okay? So what you're going to start with is you do your n times n plus 1 on 2. If we do that over here, 109 times 110 divided by 2. I'll deal with the arithmetic in a minute. But that's just finding the sum from 1 to 110. Okay, 109, apologies, from 1 to 109. Now, we're then going to subtract the sum from 1 to 25. So what you're then going to do is you're going to do the n times n plus 1 on 2, but you're going to do it for the number that's right underneath the lower bound of this range, okay? So you're then going to do n times n plus 1 on 2 again, but in this case over here, I'm going to highlight that n, okay, is 1 less, okay, than the lower bound of the range, okay? So I'll say that again. n is going to be 1 less than the lower bound of the range. I'll explain why isn't the lower bound of the range as well. Okay. When we do it appropriately, we should get uh, 25 times 26 on 2. That comes from n plus 1 on 2. Now, the problem that I usually see amongst my own students is there's always a couple people who they have this part right, and then they choose to subtract 26 times 27 on 2. So this is a big no-no. We want to be especially aware of this. Look in my notes. I wrote beware. Do not include the lower range number in the second part of the formula. But we have to ask ourselves why as well. I don't want to leave you guys and just say, oh, just don't include it, right? It's because when you do this over here, you are actually counting the 26 as well. That is problematic because 26 was part of our desirable range. We wanted to know the range of numbers from 26 to 109. We didn't want to know 27 to 109. We wanted 26 to 109. So 26 ought to not be included in the amount that we're taking away. Okay. Now, this is where the second question from students usually comes in. They go, oh, but Sophia, you wrote 26 over here. Didn't you write 26 yourself? That's what someone always asks me year after year. But you actually have to understand where that 26 comes from. Okay, everybody? So we put in 25 into n, okay? But it's just a bit of a shortcut because this part is n plus 1. So that's why it's written as 26. This 26 is not the same as this 26 over here. Yes, they're the same number, but they do not have the same origins, okay? So this 26 should really, if I want to be a bit clearer for everybody, should be written as such, okay? What you're then going to go ahead and do is solve. So I'll very quickly solve this one for everybody, okay? So I'll just write this out one more time, just so it looks a little bit more pleasant. 25, 26, and 2 over here. Just a moment. And I'm going to go in and I'm going to simplify everything just to avoid the chance of any arithmetic mistakes. Now, I only really have to do 2 multiplications and a subtraction, which isn't hard at all. I'll be doing this part on my calculator, but I do feel that everyone should definitely be able to do this by hand by the time that you guys are in year 8. So 109 times 55 is 5995, and 25 times 13 is 325. So let's go ahead. We will subtract that and we will see what we get over there. So we get 5670, which sounds very reasonable to me. That sounds good. Okay. Now, how do I test whether or not it's reasonable? You might ask as well. Well, before we just together just did 1 to 100, that's like the classic example that people are always asked when they're first learning Gauss. I remember when I learned Gauss in year 2, I think it was a challenge problem that was posed to the class as well. Unfortunately, no one in the class was as smart as Carl Friedrich Gauss, but I remember that was the very first exposure I had to this problem, and it was always 1 to 100. So we know for a fact that from 1 to 100, it is 5050. So if it's 26 to 109, yeah, we lose the first 26 numbers, but the first 26, they're kind of small anyways. Like they're 1, 2, 3, 4. They're not a lot. But then, we have the extra numbers 101, 102, 103, all the way up until 109, which are quite big. So I do expect to see a number that's a couple hundred bigger than the one from before, but not ridiculously larger. And this fits perfectly into the range. It makes sense. It looks good. Okay. So that's just a quick thing that you can do, just a quick little common sense check when you're giving your answers to just check if it's right. Now, it's a bit more of a broader way of double checking. It's not the kind of double checking that would be able to pick up on a teeny tiny mistake. So if someone accidentally had done 26, like they included 26 instead, right? Your answer would be a little bit smaller because you'd be subtracting more. That's not something the kind of double checking I just talked about would be able to actually pick up on. Well, the double checking I just talked about, that's going to be picking up on any big errors. Okay. This kind of double checking is just so you can quickly look over your problems, quickly see, at a bare minimum, does it cross that basic threshold for looking kind of all right? Okay. Anyways, we'll do the second one over here as well. I'll do this one a little bit more quickly. Yeah, over here. So you go 203 times 204 divided by 2. So just be clear, this is finding the sum of all the numbers from 1 all the way up until 203 minus 69 times 70 on 2. And this 70, it comes from 69 plus 1, okay? So what I'm doing in that second half of the equation there is I am subtracting all the numbers from 1 through to 69, okay? I get rid of that undesirable range, which is going to leave me with only 70 to 203, which is exactly what I want over there, okay? You just want to do a quick bit of simplification here, 102 and 35 here. This part I will just do on the calculator and we'll see what we get. So 203 multiplied by 102, that is going to give us a very large number, 20706 minus 69 times 35, which is 2415. So we're going to subtract those two numbers now, and we'll see what we get. We end up with 18291. Now, does that seem like a reasonable answer to me? Yes, it does, because adding up all the numbers from 1 to 2, 3, you might be thinking, well, there's only 100 more numbers than from 1 to 100. Why did it grow so much? You have to remember, from that range, from like 100 to 200, every single one of those numbers is at least 100. In fact, towards the second half of those numbers, they begin to grow very big and they become closer to 200 instead. So there's many hundreds that are being added on top of one another. So it makes sense that our numbers have grown so quickly. So that is our second answer over there. Okay, hope that's helpful to everyone. So that is how you deal with Gauss when it's in a range. The next thing that we're now going to deal with is we are going to talk about cyclic exponents. So fortunately, if you watched the previous video on cyclic patterns and you really understood everything that was going on there, cyclic exponents won't be too hard to understand. They will look kind of scary, they will look a bit intimidating, I'll admit that, but it's actually not too big of a jump from what we talked about in the previous video. You just really have to keep your wits about you, and I promise it'll be okay. So let's have a little bit of a look and let's just talk about exponents in general. I'll deal with negative exponents first. Now, for negative exponents, there's actually often a lot of confusion with even the basic questions for many students. Many students, even in year 8, 9, 10, are actually unable to tell me the difference between these two equations over here. It's important you know what is the difference here and what we're actually dealing with in order to be able to understand some of the questions we're going to be doing today. Okay, so this bottom example, if you take a closer look, you'll see that the entirety of -2 is inside of those brackets. So what those brackets are signaling to us is, hey, the entire base number here is -2. And of course, we know our power tells us how many times we've got to multiply that number by itself. So this means -2 raised to the power of 2. So when you spread it out and you do it properly, it's -2 times -2, which gives us 4. Okay, everybody? Now that is actually a different situation to the first one that I've drawn up over here. Okay? This negative, you'll see it's not protected by those brackets over there. That negative is actually separate from the two. Instead, the way that you should actually view that example is it should really look something like that. Okay, that would be a more nicer way to put it over here. It'll look a little bit more pleasant when it's like this. Okay, so this is really actually just -1 times 2 to the power of 2, if that makes anyone feel better. So you get -1 times 4 and you get -4. Okay, so it's very important that people understand the placement of where those brackets are, the placement of that negative. It does make a difference to our final equation answer there. Now, there are some cases, granted, where you'll get the same answer regardless of where the brackets are. For example, I'll give one for you now. -4 to the power of 3 versus -4 in brackets to the power of 3 over here. Top one is -1 times 4 to the power of 3, which is -1 times 4 times 4 times 4. Now, 16 times 4, I believe that's 64. So you should get -64 over there. right? Now, in the second example, that's actually -4 protected by brackets to the power 3. So what that actually looks like is -4 times -4 times -4. And so then you get -64 because you have three sets of negatives with each other. So in this second example I give to all of you, you get the same answer from either of these, okay? But what you really want to make sure you understand is yes, we get the same answer, but we got there in different ways. That's really crucial and that will really help you understand what we're going to look at now. Okay. What we're going to deal with is we're going to deal with the case of -1. Okay. A question that they often like to ask is what is -1 to the power of some absurdly large number? Let's choose 1827 over here. Okay. Now, a lot of students, they're going to see this. They're going to go, I have never seen an exponent so large. I've never seen a power so large. And they skip it or they begin trying to do it. And then they end up wasting time. They get really confused and stressed out. So there are two things that we need to know in order to be able to do this particular problem. Firstly, how ones work. Okay. Anything that has a base of 1, okay, 1 raised to the power of anything, 100, 1 raised to the power of 1,000, a million, so on, is always going to equal 1 itself. Because if you think about 1 to the power of 100, it's just 1 times itself 100 times. Anything times 1, no matter how big the number is just going to end up being itself. If in this case 1 is just timesing itself, it's just always going to come out to be 1. Okay? That's sort of thing number one. Thing number two, what about -1? Okay. Well, let's see, and let's just test out a few to see what's going on. You probably have heard me say this a few times now, but let's do a little experiment and let's just see what's going on. So, -1 to the power of 1, let's see, okay, is equal to -1. -1 to the power of 2 equals 1, +1. -1 to the power of 3. We can write out the full thing over here. Oh, -1. And let's do one more for good measure. -1 to the power of 4. -1 times -1 times -1 times -1. Okay? It is going to be +1. Okay? So that's the second thing we have to know. It's always just going to come out to be either -1 or 1. It's not going to be some massive answer. Sometimes some students get confused and they tend to think, ooh, maybe it could be something like 1827 or some giant number. That's not the case at all. So right now, right off the bat, we know the answer is either going to be 1 or it's going to be -1, which is reassuring for everyone. You don't have to do some massive equation. But now that begs another question. Well, which is it? Is it 1 or is it -1? Well, we'll actually return back to our little experiment here. And I want to encourage everyone to just take a moment, just have a look, pause the video if you need to. Can you see any pattern in this little experiment we've done? Okay. I think I can see a pattern. Now, I'll give it away for everybody. So if you're trying to still make a bit of a guess, pause the video. You might even want to write it down, write a little hypothesis in your book if you really would like to, but I'll give it away now. Okay. The pattern is when you have a negative number, so a negative base raised to a odd exponent, okay, over here, you see I've sort of raised it, raised to an odd exponent, you are going to get a negative answer, okay? And when you have the same negative base, except it's being raised to an even exponent, what we're going to see and what we're going to get is a positive answer. Okay? And you can test this out with just the four we have over here. We can see that being true. Okay? But how come? Why is this true? We don't want to just accept it. Don't accept it just because I tell you as well, everyone. I want you to question it for yourself. Why exactly is this true? Well, look for yourself. When something's raised to an odd exponent, we have an odd amount of powers. For example, with the 3 over here. Oh, sorry, not an odd amount of powers, odd amount of negative signs, my bad. So you have 1, 2, 3 negative signs. Now we know from our basic multiplication, our negative multiplication, that when you have two negatives, they cancel out and make a positive. Okay? But say if you had like 3 of them in a row, well, we would have a positive here, but a negative over here, which makes it ultimately negative. Okay? Whereas an example where there's an even amount of exponents, like 4 here, 1, 2, they make a happy little pair. 1, 2, they make a happy little pair. And everything is all positive and even positive when things are even. So that's why that's the case. Okay. So if we go back to -1 to the power of 1827, the ultimate answer over here is we've got a negative base raised to an older exponent. It's going to be a negative answer. Couple that with what we learned from these two steps over here, the answer was either going to be -1 or 1. In this case, it is going to come out to be -1. So I hope that helps everybody. Okay. One last thing to touch on now is actually cyclic exponents. Okay. So cyclic exponents are actually not too hard to do at all. Now, typically, if they do ask you to do it, they usually won't actually ask you the exact answer. So here I have 4 sample questions. Okay. I am not going to be asking anyone to figure out for me what 2 to the power of 1,000 is. That would just be absurd. It would be a waste of everybody's time. If you try to put that into the calculator, I'm pretty sure the calculator won't give you a proper answer as well. It'll come up with some funny symbols because even most calculators themselves can't display that many digits. So we relax. We're not going to ask anyone to do 2 to the power of 1,000. However, you could be asked to figure out what the last digit is, or if it's a worded equation, oh, what will it land on, or something along those lines. Okay? So let's do 2 to the power of 1,000. And they're asking us to determine the last digit. Okay? So what we do is we actually first determine the n digit pattern. What do I mean by this? Well, let's go back. Let's do another experiment again. So we'll just do 2 to the power of the first couple. So 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8 over there. 2 to the power of 4 is 16. I'll list out a few more for good measure, just because this is the first one that I am showing everybody. So let's list them out. Hope I don't make a calculation mistake over here. 128 and 256. There we go. Okay. I remember those because I like to play the game 2048 a lot. But yeah, over here, let's have a look. Can we spot any pattern with the last digits? Why, yes, we can. 2, 4, 8, 6, 2, 4, 8, 6. So that is our pattern. So let's write that down. 2, 4, 8, 6. Now we are raising 2 to the power of 1,000. So it basically means go through this pattern just 1,000 times. So if we did 2 to the power of 4, we'd go 2, 4, 8, 6. If we did 2 to the power of 7, 2, 4, 8, 6, 2, 4, 8, and we'd end on 8. And now, particularly if you're someone who watched the previous video, you can probably see what direction this is heading under, okay, or heading towards. We have these 4 numbers. We're going to go through it 1,000 times. What do we end up on? And so the exact same ideas from that previous video now apply, okay? So you just do 1,000 divided by 4, and you end up with a perfect 250. Wonderful. So if it's a nice round number like that, no remainders, it is just simply going to be the last digit, which is 6. Now, please beware here. I've seen this a lot. I've done this myself, I'll admit. My students have done this a lot as well, is when it's a nice even number like this, there's no remainders. A lot of students will tend to jump to 2 because they think, oh, perfect cycle. We've gone through the pattern 250 times. Unfortunately, that's not the case, okay, everyone? If you're a little unsure, once again, do a little experiment yourself. Imagine if it was 2 to the power of 8 instead. Well, you'd do 8 divided by 4, and you would get 2. Well, we know 2 to the power of 8, it ends perfectly on a 6 there. So you can see in this case, when it's a perfect, nice little cycle, you end on the last digit. So I know 1,000 looks really scary, but you have to ask yourself critically, why would it be any different? It's no different, okay, is the answer to that. You'll end on a 6 over there as well. So yeah, that's how it goes. So we'll do some of the others as well. I'll show you everyone 3 more problems to just make sure the message really sticks, okay? I'll erase a little bit of this working out to create a bit more room, okay? Let me write out this pattern for 2s, okay? And we'll do 4, okay? 4 to the power of 1 is 4. 4 to the power of 2 is 16. 4 to the power of 3 is 64. 4 to the power of 4. 64 times 4. I'll do that here. 256. Okay? So we can see a pattern. 4, 6, 4, 6. Now, if you're feeling really sharp, everyone, you might even notice that, when it's an odd exponent, it's 4. When it's an even exponent, it's 6. And so some students who are really on top of it, they'll see 1,039. They'll know that it's an odd number. So therefore, we ought to end on a 4. But, not everyone's always that sharp, so we can do it our other way as well. We know our pattern is 4, 6, 4, 6. I just write out just one set of the pattern. I know this is a very short pattern. There are only two numbers, but I'm only going to write out two over there. You could do 4 theoretically, or you could do 6 or an odd number as well, but 2 just keeps it simple because there are only two numbers in this pattern. I wouldn't go and create any more trouble for myself, okay? 1039 divided by 2. 2 times 5 is 10. 2 times 1 is 2, leaving you a 19. 2 times 9 is 18, remainder 1. So 519, that is 519 perfect cycles. 4, 6, 4, 6, 4, 6, 4, 6. Again, 519 times. On the 519th time, you land on the 6. It finishes there. And then one more, which is how we get to the 4, which is what I said already. Okay, so there's that. Let's do the 3s as well. Okay, so same thing. We do a little experiment on the side and we see how many there are. Okay. Now, usually for me, I will just go about 4 or 5 numbers in. Now, granted, when you've done a few of these problems already, you will see roughly you will understand and remember roughly what the patterns are. So, for example, I've done this enough times to know the patterns 2, 4, 8, 6, 4, 6, 4, 6. For you, if you're trying this for the first time, you might want to take a moment after this video to just list out a few and see what the patterns are roughly, and you'll remember them roughly for next time. But you don't need to list out too many. You definitely don't need to do 10. Usually just doing 4 or 5 is enough, maximum. Okay, so over here, 81 times 3. What is 81 times 3? We'll see. It's 243 over there. Okay, I can see a pattern. It's 3971, 3971. Okay, and so on. So what we can do over here is the pattern consists of 4 numbers. We'll do the 1692 divided by 4. 4 times 4, 4 times 2, 4 times 3. Oh, this is a perfect set. It's going to end on 1 over here. And we'll do one more for good measure. Now, 5 is actually a really easy one, and I'll show everyone why. 5 to the power of 1 is 5. 5 to the power of 2 is 25. 5 to the power of 3 is 125. You can see the pattern. It is always 5, so we can just answer 5 over here. Let me give you just one more trick over here as well, guys, when you're dealing with very large exponents, okay? Or very large multiplications in general. A lot of times, you actually don't need to do the whole thing, okay? And that's a technique that's reserved specifically for this style of exams. Obviously, at school, if you have to do a large multiplication, go ahead and do it. You will lose marks if you don't do it. But for an exam like this, ask yourself, do I really need to do that giant multiplication? For example, if someone asks you, oh, 3 to the power of 6 or something, and I don't feel like doing 243 times 3, I can just do this. 243 times 3. Well, I know multiplication. I get 9. I'm going to get a bunch of stuff over here. The end digit's just going to be 9, okay? If I look through the answers and one of them ends on a 9, I'll just pick that one. That's just for general multiplication. If someone asks me to do 1, 2, let's say 1, 2, 3, 4 times 4, 5, 6, 7, I'm not going to do that. I just do 4 times 7 is 28. I know that my final digit in the entire multiplication will be an 8. So I just look through the answers and I see if there's any answer that ends in an 8. So that's just another little tip that can make your life a bit easier. Okay, so thank you so much for watching, everyone. I know this is a bit of a longer video. We've got 58 days left until the exam at the time of filming. So good luck, everyone. Thank you for watching. Good luck for the exam, and feel free to drop any questions you have at all in the comments. All right, have a great rest of your day. Thank you, everyone.